stuff there, learning goals, etc. Oh, I better just check sound. I have, yep. Okay, let me just tell you a little story to start with. This is a project I used to do with some Year 9s about a guy called Eratosthenes, who's around about, I could get this wrong and I'm recording it, but I'm going to say 400 or 500 BC. And he lived in North Africa. At the time, it was very early Roman Empire time, but they weren't part of the Roman Empire yet. And he was a trader. And he noticed that in a well that he lived near in North Africa, the sunlight in the middle of the day would create an angle in the well. So it would look a bit like, I'll draw it on here. So that would be the well, and the sunlight would come down here, and he could see the shadow was at an angle. And he noticed that when he travelled, because he was a trader, when he travelled south, the sunlight reflected slightly differently. So if you imagine a situation with the Earth, the sunlight would reflect like that and create a different angle. And he also knew how far he travelled. And he used that knowledge and the position of the sun and the fact that this was further away from the equator than that to estimate the circumference of the Earth. And in his estimate was within a couple of 100 kilometres of the actual circumference of the Earth and wasn't beaten again until the 18th century. So it went his estimate, which is recorded, and the mathematics he did, which was recorded based on similar triangles, trigonometry and Earth geometry. And his estimate lasted for 10 years. Other people made their estimates based on other different elements of astronomy, and they were far worse for 2,000 years. And it was only until we got modern technology that we actually managed to get a estimate of the circumference of the Earth. And it was all just based on some really simple maths and shadows and stuff like that. A really cool intro to trigonometry topic that suits the Year 9 group and that kind of area there, but it's a really interesting story as well. That was a struggle to get in the door there. Thanks. Okay, so your learning goals are to understand the relationship between decimal and degrees and minutes. So you'll need to be able to do that conversion. We typically use decimal now, but degrees and minutes comes up, and we can talk about how to do it in a calculator. Arc, minor arc, major arc, and subtending an arc. You'll need to be able to calculate an arc length, which I'll explain to you as well once we talk about arcs, and also angular notation. So these are things that are going to come up in the Earth geometry topic, so you need to be aware of them. Degrees versus degrees and minutes. So let's talk about that very quickly. And I'm just going to scoot down to here, and you can go back and copy some stuff down later if you want. Here is degrees and degree minutes. So when we're talking about degrees in decimal form, we get something like this one here, which is 34.5 degrees. That's 34.5 degrees. If we write that in degree, minutes and seconds form, you have to remember that the degrees will be the same, but the seconds and the minutes are out of 60, not a decimal form out of 100. So if we've got 34.5 degrees, that's 34 degrees and half of 60 minutes, which gives you 34 degrees and 30 minutes, which is why we get this notation here. So you'll need to be able to do that conversion as you go through these types of questions. 34.25 is 34.25, and that's 34 degrees and 15 minutes. And 34.75, same thing again, but you will need to be able to do it pen on paper as well. So here's an example of that. If we needed to convert 42 points to degrees and minutes, then the 42 itself stays the same. 42 whole degrees will remain 42 whole degrees. But the 0.3 degrees, we get that 0.3 and we multiply it by 60 minutes. And that will give us 18 minutes. So 0.3 of a whole degree is 18 minutes. It's 3/10 of a 60-minute cycle there. And so we get 42 degrees and 18 minutes. I suggest you grab your calculator and just try that out. Make sure that you understand that 42.3 degrees, we start by just removing the whole number with 0.3 and 42 minutes is still there. This 0.3 is multiplied by 60 and that gives us 18. And so now we have 42 degrees and 18 minutes. Now, I might just quickly show you one other example, and it really is unlikely that you're going to get gets that complex. But just as an extension to this, 42.3 is really nice because it converts directly to a whole number of minutes, but it might not convert directly to a whole number of minutes. You might be dealing instead with something like 42.28 degrees. And I'm going to need your help a little bit with this one. 42.28 degrees, we have 42 whole degrees, so I might write this down here. Degrees is 42, and we're left with 0.28. So we get the 0.28 and multiply it by 60. Somebody help me out. What is it, sorry? 16.8 minutes, but I don't want to use 16.8 minutes because I want these to be whole numbers. So I have 16 whole minutes, and I'm left with 0.8. And there are 60 seconds in a minute, so I multiply that by 60, and I get the number of seconds, which is my double dash notation, is 48. So 42.28 degrees is equal to 42 degrees, 16 minutes, and 48 seconds. We don't go below seconds, so if there is still a decimal remaining, we round appropriately and we leave that there. Is anybody got any questions on that? Can I borrow, Morgan, can I borrow your calculator? On your calculator, which you will have in all of your exams for the entire time, it's only really a problem if you're asked to show working for why something is equal to something else. If you just quickly grab your calculator, there is a degrees, minutes, second button here. It's below the square root sign. If you go to the square root sign, you've got a circle, comma, double comma, or apostrophe, double apostrophe. And that will convert. That's how you can represent degrees, minutes, seconds. So I can put in 42, press that button, gives me 42 degrees. And then 16, press that button, does the minutes. And then 48, press that button, we'll do it in seconds. And press enter, and I've got that represented as degrees, minutes, seconds. And if I press that button again, it will convert it back to decimal form. So try that out. Put it in. Now press the decimal form button. I can convert it back to degrees, minutes, seconds. Put in any number you want. I'm going to put in 58.296. And if I press that degrees, minutes, second button, it tells me that that's 58 degrees, 17 seconds, and 17 minutes and 45.6 seconds. So that button will do everything for you. It's the one below the square root sign. And I'd suggest you try it out now. But you might be asked to do pen and paper. So equally, converting from degrees, minutes, seconds back into decimal form works the opposite way. So in the previous question, we multiplied the decimal component by 60. In this form, we get the minutes and we divide that by 60, and that will represent the number of, or the decimal component. So as the example shows here, 35 degrees and 12 minutes becomes 35 degrees and 12 sixtieths of a minute, which is 35.2 degrees. So we do that conversion here. An additional example, maybe a little bit harder, will be 35 degrees, 11 minutes and 17 seconds. This is equal to, this part of the conversion is a bit easier. It's 35 whole degrees plus 11 minutes plus 17. Convert to minutes by dividing by 60, and then convert to degrees by dividing further 60, and that will give us our decimal form. The seconds don't contribute much decimal-wise, but we can still do that calculation and be accurate. 35 plus 11 over 60 plus the number of seconds over 60 times 60, which is 3,600, sorry, and I get 35.188 degrees. So make sure you can do those two questions. They may come up pen on paper, particularly when it comes to the external exam. Okay, I'm going to run through now calculating length on an arc. So here's some definitions. There's a diagram for you. It's also defining your textbook with similar diagrams. So first of all, you've got two arcs on a circle. The arcs are around the outside of the circle, but they're not the whole circumference. So they're usually arcs are subtended by an angle. If we know this angle, that subtends a specific arc. But once you create an angle here, there's obviously a small angle, in this case the acute angle, and then there's a large angle here, which is our reflex angle. So there's two arcs. There's the red arc and the black arc. The red arc is called the minor arc, the smaller arc is the minor arc, the larger arc is called the major arc. So what's going to happen is most of your questions, pretty much all of your questions, are going to be Earth geometry based, but you might have to calculate the distance a ship sails around the globe on the major arc from this city to this city, which just means that on the globe, if the ship starts here and finishes there, the major arc is going the long way of the Earth, not the short way. So you'll need to know and understand that language even for the context. Semicircle, a circle. Any questions? There's some language as well. So arc AB subtends, that's that special word, subtends angle BCA. Subtends might come up in a theoretical question. It won't have to do with Earth geometry. And it is referenced in a syllabus, so just get used to that language as well. How do you think, just think about this, because this is not a memory game now, you don't have to memorise anything because it's very logical. How do you think we would find the length of that red line, which is going to be a distance question on here? How would you do it? So? No? You've got to fill the gap because this is going to become really annoying on a video of just blank time. How would you find the length of any of those red? How would you find the length of the one in the middle? If I said the radius is 10, how would you find the length of it? So you get the circumference, you divide it by 2. Can you see that? That red one there, semicircle, the red length would be the circumference divided by 2. This is the same for the minor and the major arc, except it's just a proportion based. So if this angle here was 60 degrees, 60 out of 360 is 1/6. That red line would be 1/6 of the circumference. Yeah? If this angle here was 52 degrees, that's obvious, but is 52 3/60ths of the circle. So that red line will be 52 3/60ths of the circumference. So if I just go down here, here's the formula. The arc length, which is often called S, is equal to theta over 360 times 2 pi r. What's 2 pi r? 2 pi r is our circumference formula. So the arc length is equal to theta, the angle divided by 360, that gives you the proportion, times by the circumference, which we can calculate by doing 2 pi r. Any questions on that? Here's an example. Let's calculate the length of the arc ACB. Do you see how I've just named that arc by calling the end point to the arc and one point in the middle? That tells you it's the minor arc or the major arc. So in the circle centre O, if you see O, it will always be the centre. Radius 10, the angle subtended by O and by arc ACB has a magnitude of 120. Find the length of arc ACB correct to 1 decimal place. I'll need your help here, but the length of the arc is going to be equal to S will be 120 3/60ths times by the circumference, which is 2 pi, times the radius, which is 10, and that's a third of 2 pi times 10. It says to 1 decimal place, so we're not keeping an exact formula. 120 over 360 times 2 times pi times 10 is equal to 20 pi on 3, which is equal to 20.9. 1 decimal place, 20.9, and it's in centimetres. Can you ever see that? So these questions are fairly procedural that you're going to be. And that's it. That's me. I'm going to stop this.